Okay, so the plan for today, we're going to do a little more work in probability and then kick some of the information to a supplement and then start on chapters 9 and 17 on differential equations, where we'll be for the next few class meetings. Um, as I've kind of mentioned, I think in both of these topics, um, probability really could be at least a whole semester course, probably, even more than that. Well, certainly even more than that. Um, and same with differential equations. So in both of these cases, these are meant to be more expository, probability more so, but also differential equations. We're certainly not um, going through the material as rigorously, as thoroughly, as carefully, with as many examples or whatever, as we would in, say, a purpose-made differential equations course, which we offer here at CCAC. So if you kind of like what you see and you want more information about it, differential equations course is a good place to go. If you look at this and you think, wow, that's just like too much information too quickly, I could never do DiffEQ or something, or you're really struggling with it, don't really take these next couple lectures as a barometer for differential equations overall. Again, these are more meant to be expository lectures and show you some interesting ideas. And a regular DiffEQ course would take um, probably the better part, probably the better part of 2 months, a month and a half or so, to cover the material that we're going to cover in about 3 class periods. Now, of course, like I said, it would be covered at a greater depth, a lot more examples, more breadth. So it's not like we're not squeezing a legitimate month and a half of material into 3 lectures, but we're kind of touching on some high points here and there that we're selecting out of those ideas. Okay, so that is the plan for today. The quote of the day today, it's a bit of a longer one. It comes from a YouTuber, Alec Watson, from the channel Technology Connections. Mostly what he posts is things like everyday objects that are seemingly simple in nature that have interesting engineering in them. So like things like a coffee maker or uh, like just a regular old fan, just like a little, desk fan that spins around and blows air. Um, so just the interesting little engineering solutions that enable these to be simple, easy to use, very reliable, made very cheaply, um, and a lot of times have more interesting engineering to make all of those things happen, and safe, of course, like than you might realize at first glance. So this little, goofy $12 coffee maker, uses some interesting ideas to make it cheap and reliable and consistent and easy to use and all of that. Um, so mostly that's what he posts, but he did a little bit of a different video this past weekend on kind of AI and particularly how we interact with AI. And I really like this kind of quote or this idea from that video. Um, so his quote is succumbing to algorithmic complacency, which is kind of the term that he gave to where things like TikTok or YouTube will recommend things to us, these recommender systems that say, hey, you might want to watch this video. And not just that we're okay with that, but that we actually prefer that to choosing our own direction, choosing our own way of interacting with this content. So succumbing to algorithmic complacency means you're surrendering your own agency, your own kind of ability to make choices, or in some sense, your own humanity, really, in ways you may not realize. And as the internet and real life continue to blend together, which I think we all are seeing that, real life, the kind of physical reality, uh, is more and more things are getting replaced by not virtual reality per se, but virtual types of realities. That can end very badly. I think this is an example he used, but I was thinking about this. Like, I think most of us would be pretty suspicious about, say, getting into a car and just telling it, take me somewhere that you think I'd enjoy going, even if we trusted that the car wasn't going to wreck us or something, right? I think very few people, you know, to give another example, would just be willing to like set a timer on their phone and get on a bus or some random bus or trolley or something like that and say, okay, when 30 minutes goes off, I'm going to get off the bus and kind of look around, right? Um, we want to do that in the physical reality, but we almost prefer that happening in the virtual world. And so he continues, today's internet is shaping how we view the world and how we operate within it. We're largely no longer in control of what we see. And I think this is a really good point, is just being careful how we interact with these recommender systems in particular, knowing that for better or worse, the purpose of these systems is to keep us engaged, right? To keep us clicking more or viewing more or whatever. I mean, in some sense, people say this is the big corporate overlords trying to milk us for profits, but in another sense, this is implicitly and often even explicitly what we ask for, right? When we have the choice of, say, using subscriptions or playlists on YouTube versus using the like whatever, recommended for me feed, most people use the recommended for me feed, and they get, 3 hours later they come up from their deep dive into cat videos or whatever it was. So sometimes that can be fun, but just being aware of that, cognizant of that, and maybe a little bit careful about how much we use that in and what ways we use that technology. So that's kind of the thought for today. Usually I try to pick things that are a little more abstract and philosophical or something that you can take different ways, um, but I saw that and I thought that was a very valid point these days. So, okay. So continuing with probability, just a super quick refresher because it has been 5 days. We're talking about continuous random variables here. That's kind of the interesting case for calculus. That's not to say that discrete is not interesting, but it's just not the focus of our course. Of course, calculus being interested in continuous functions, but discrete probability has very many applications, and in a probability course, it would be dealt with much more thoroughly. We describe a random variable using its probability density function. This gives a linear density of probability that really only makes sense in some loose manner of speaking when it's accumulated over a linear distance. So we can say the amount of probability is like the accumulation of the probability density over a linear distance, or it's the integral from A to B of the PDF. That would be the probability of event E that our random variable ends up between A and B. Recall that the probability that our random variable ends up exactly at a given number is 0, because that's integral A to A of the density. That's kind of like we have a linear rod that's, 2 pounds per foot, but we have 0 feet of that rod. Well, that we have 0 pounds, then we have 0 weight. But if we cut off a chunk of that rod that's, 1 foot long, then it weighs 2 pounds. So to get probability, we accumulate probability density over a linear distance. We talked briefly about the CDF and the relation between the CDF and PDF. And we had some canonical distributions. These are distributions that have a lot of modeling applications and also where the math works out pretty nicely. There are some distributions that are nice for modeling, but where the math is, a huge hassle, or maybe some other distributions where maybe the math would work out nicely, but you're like, when am I ever going to use this? But these all have kind of underlying statistical reasons that they are useful distributions, so they're ones that are used often. This is by no means to imply that these are, the only distributions or anything like that. That's certainly not the case, but these are certainly ones that will come up quite often in any kind of either probability theory course or engineering statistics course, anything like that. The uniform distribution, just the distribution that has constant probability density over a region. The exponential distribution, an exponential decay on the positive side and 0 on the negative side. And our bell curves, the standard normal distribution centered at 0, inflection points at plus or minus 1. And our general normal distribution that has parameters mu and sigma squared, also a bell-shaped distribution. Centered at mu, so we call mu the location parameter. It turns out to be the expected value of the distribution or the mean of the distribution. And these inflection points are sigma away. The standard and general normal distributions have this nice kind of evenness type symmetry. The standard normal distribution is actually an even function, symmetric about the y-axis, about the zero axis. And the general normal distribution is symmetric about the axis x equals mu. Or I suppose in this case, w equals mu. Okay, let's compute a couple of probabilities. Let's talk about expected value. We'll probably compute the expected value for maybe 2 of the canonical distributions and leave the others as exercises. And then we'll kick to the supplement discussing median, variance, and standard deviation, and that will wrap up our discussion of probability for this course. Okay, so when x is uniform, let's just copy this down. Maybe I think I can actually just pop it over here. Yeah, off to the side. So x is uniform on 0 to 15. This might be a model for something like, say, the amount of time I expect to have to wait at a train station. I know the train comes every 15 minutes, but I don't know exactly what the schedule is, what times it's supposed to show up. I show up at the train station, I might step on the platform right as the train gets there and have to wait no time at all. Or I might step on the platform just as the train left and have to wait 15 minutes, or maybe somewhere in between. And I really have no good reason to suspect that, one side of things, earlier or later is going to be more likely than any other. And this probability that x is between 1 and 5 is the question, well, what's the probability I have to wait between 1 and 5 minutes for the next train to show up? So x is uniform on 0 to 15. Let's draw a picture of that. So here's 0 and 15. My PDF has constant height on 0 to 15 and then height 0 outside of that. I noticed that this is just a rectangle with a base width of 15. So it has to have height 1/15. Remember that one of the criteria, kind of the main criterion for a PDF, is that it has to integrate to 1. The total area under the curve has to be 1. And of course, with this just being a rectangle, it's easy enough for us to see that base width of 15 means we have to have a height of 1/15 to make that work. This is, to be clear, remember this is our PDF. This is a density, a linear density. So areas under this curve represent probabilities. Accumulating over this linear density across a linear distance is what gives us probability. So we are looking at the event x being between 1 and 5, waiting between 1 and 5 minutes. And our question is, what is this area? Well, of course, we see this is just the integral 1 to 5 of fx of x dx. On the entire interval 1 to 5, well, my PDF is just a constant, just 1/15 dx. This is just 1/15 times 5 minus 1, or 4/15. Something I might notice about the uniform distribution is the probability of an event is only related to essentially the width of that event, right? 1 to 5 is a 4-unit width. If I was looking at 9 to 13, that would be the same. If I probability that I would have to wait between 9 and 13 minutes, that would be the same probability for unit width, or from 7 to 11, or from 3 to 7, or any 4-unit width for this particular uniform distribution is going to have a probability of 4/15. Now, I have to be a little bit careful if I was looking at, say, 13 to 17. Well, 13 to 15 is the only place that I accumulate probability, and then 15 to 17, I don't have any. So it's not any 4-unit interval, it's any 4-unit interval that stays strictly between 0 and 15. If I fall outside of there, then it's going to be 0 for at least part of that interval for the PDF, so then I would change my integral accordingly. But I see there's a 4 out of 15 chance that I'll wait between 1 and 5 minutes for the next train to show up for this specific uniform distribution. It is important that I have parameters like alpha and beta here so I can tune this, right? Maybe I go to a different train station and that one comes every 20 minutes. I can keep alpha at 0, beta can jump up to 20. Uh, so uh, yeah, I think that is all that I have to say on this one. Any questions on this one? Now this one, of course, the uniform distribution is easy enough that we could just figure out this area algebraically or geometrically. Let's look at the exponential distribution. Let's grab the exponential distribution, bring it down. Okay, so I see here that y is exponential with parameter 1 over 10, lambda equals 1/10. And I want to compute the probability that y is between 0 and 20. Okay, I know that my exponential distribution to the left of 0 is just 0, so I'll just kind of note that here, but we're really interested in the right of 0. And I'm interested in the probability of y is between 0 and 20. So I'll start here and go up to 20. Again, remember that this green curve represents a PDF. It's a probability density. So accumulating it over a linear distance, so linear density accumulating over a linear distance, say 0 to 20, is what gives me an amount of probability or a likelihood or a chance that this occurs, that this random variable y turns out to be between 0 and 20. Or that's integral, oh, let me switch back to blue, integral 0 to 20 of, well, of the PDF, which is lambda e to the negative lambda y dy. Here I'm just going to keep things as in terms of lambda, I suppose. If I integrate this, what do I get? I get e to the minus lambda y. I get a lambda in front coming down from here. If I differentiate e to the minus lambda y, I get negative lambda, so I need a negative 1 over lambda to fix that. These go away. And I'm evaluating this from 0 to 20, from y equals 0 to 20. Or this is negative 1 times e to the minus 20 lambda. Now I'll put in my lambda as 1/10 minus e to the minus, well, 0 lambda is just e to the 0 or 1. 1 minus e to the negative 2. That one I could not have found with just basic geometry or algebra. I really did need the calculus to to solve this problem. But we see that it turns out to just be a fairly straightforward integration problem. Any questions on that one? Okay, so what is the expected value of a random variable? There's some nuance here about what is an expected value, but essentially it's just an average. The same way that if I had, 20 students in a class and you say each took an exam and I might report to you the average score from that exam, I would just kind of take each of your scores, add them together, divide by the total, and that would be the average score. Well, kind of what a random variable with a PDF that's not constant is, it's kind of like taking each of these 20 students and weighting them differently. I'm going to take this student's score and triple it, and that student's score and divide it in two, and then I'm going to kind of take that weighted average. So I'm weighting certain results differently than other results. So I kind of have the weighting is given in a sense by this PDF. This is like the weight. And then this factor of X in front here is like the result itself. So if I was to take a weighted average, another way to think of that is, at the end of the semester, you look at your syllabus and it's like, your homework score times 40% plus your, say, midterm exam score times 30% plus your final exam score times 30%. Those three results, homework, midterm, final, are weighted differently, 40, 30, 30. So it's kind of like we take the weight times the result, take that product and add it together. That's what we do in the discrete case. In the continuous case, we do the same thing. We take a density that's acting as the weight times the result times the value of the random variable there, multiply the two together. And then instead of summing, like we would do discretely, we integrate continuously. Again, we would talk a lot more about this, how to go from the discrete to the continuous case and the details behind that a little bit more in a probability theory course, but kind of hitting the high points here. But the important idea is that the expected value is really just the average. It kind of answers, in a sense, the question, I have this particular random variable. If I have one kind of run of this random variable, I walk up to the train station one time, kind of on average, how long do I think I'm going to have to wait for this uniformly distributed random variable? Or I have, classic example of an exponential distribution is a light bulb burning out. How much time does it take for the light bulb to burn out? At least for incandescent light bulbs, maybe not for LEDs anymore. But that was kind of a classic example. So I screw in my light bulb, I turn it on. On average, how much time do I take, or do I expect to have before I have to replace that light bulb? Maybe it is the expected value of an exponential distribution. And the way I get that is I integrate minus infinity to infinity. Note that it's not just the PDF, but it's the variable times the PDF. So x times fx of x. The integral of the PDF itself just turns out to be 1, but the integral of x times fx is our expected value. Couple of notes. The expected value is linear. That is, if I take my random variable, multiply by some constant and add some constant, those constants just come out. This it's not hard at all to prove based on this integral here. Just take this little x, this one here, and make it a times x plus b in parentheses, and split your integral into two integrals, one with the b, one with the a. The a can come out of the integral, and some little magic will happen with the b. Go through it as an exercise and see if you can prove this. Not hard to prove. Second note, we often denote the expected value by mu, and we often call it the mean or the average, the expected value, they all kind of mean the same thing. In fact, if you go up here to the general normal distribution, you might see that one of our parameters was called mu, and there's no coincidence that that's called mu. That is the mean of the general normal distribution. This parameter here, this kind of center point, this point of symmetry is the mean. It's the average, it's the expected value. Third note, the expected value of a function of a random variable, which is kind of what this is, right? Number times x plus number really is a function of x. If I have the expected value of, say, g of x, that g just hits the x in front here. My PDF stays the same. I don't want to apply the transformation to my PDF because my PDF has to integrate to 1. If I go transforming it, it's not going to integrate to 1 anymore. Kind of the weights stay the same, but the variable is what changes. If I told you that I doubled all of your scores because I was feeling super nice that day or something, you wouldn't say, okay, now I have like double my homework score times 80% plus double my midterm times 60% plus double my final times 60%. No, it would be double my homework score times 40%. That 40% stays the same. Double my midterm score times 30%, double my final exam score times 30%. And a fourth note, we might kind of recognize this integral xf of x dx. That looks a lot like a center of mass or a centroid. Now, normally we would have to divide by integral f of x dx, right, to get a center of mass, but wait, we specifically chose little f here. We specifically chose our PDFs so that they integrate to 1. So really, if I do my center of mass and I get the moment over the mass, but here the equivalent of mass is just total probability, which is 1. So I don't have to have these, denominators of whatever floating around everywhere, right? So our center of mass looked like x bar equals integral xf over integral f, but this is just 1 when we're in probability. So really, our expected value is just like a moment. And in fact, x bar, the terminology for the centroid, is also often used in different contexts to mean the expected value or the mean or mu or the average. These all tie together very closely. This really is just, the expected values really is just the center of mass or the centroid of the PDF. Of the distribution, when I say distribution, I mean PDF. So there is some close tie-in here to moments and centers of mass. And in fact, in probability language, often even the mean is called something like the first moment of the distribution. The standard deviation, or really the variance, is called something like the second centralized moment. So these relate to and are even kind of generalizations of moments from the moments and centers of mass idea. Okay, so let's compute expected values for, we're not going to do for each of, I'll leave a couple of them as exercises, but for some of the canonical distributions. Uniform distribution. This one is super easy. I want to compute an expected value, but I remember, wait, that's just the centroid. That's just, well, it's the x location of the centroid of this distribution. But this is symmetric about an axis. I know if I have a line of symmetry, the centroid has to lie on it. So I know that my mean, or the expected value of x, has to be alpha plus beta over 2. Right? I don't have to do any calculus at all. That's just what it is, alpha plus beta over 2. If I have a train that comes every 15 minutes, I walk up to the platform and I impose a uniform distribution on this system, and that's how I model it. On average, how long will I have to wait? 0 plus 15 over 2, 7.5 minutes on average. Okay. Let's come back to exponential. What about standard normal distribution? Well, again, I actually noticed that I'm symmetric about 0. This is an even function. If the mean exists, if the center of mass exists, it's got to be 0. Indeed, it does. The expected value of z, which is the name that I gave this distribution, is 0. We're going to kind of take on faith that these tails go to 0 fast enough. We don't quite have the underlying math to prove that carefully. That's more of a Calc 3 topic. You go into polar coordinates in 2 dimensions, and then you can prove this pretty easily. And similarly here, you might notice, as I said, mu, we chose the name for that name for the location parameter because it is indeed the expected value of this distribution. It is the average. So the interesting one of these to do kind of by hand, so to speak, or in long form down here, is the exponential distribution. So again, for the exponential distribution, I have something looks like this, and then of course 0 on the left. Where's my centroid going to be? It's not going to be way off to the right. It's, looks like it's going to be kind of somewhere, somewhat close to 0. There's a lot more mass close to 0 than there is way out in that tail. So the expected value of x is the integral minus infinity to infinity x, or I gave this the name y. Let's use the right name for it. The expected value of y is integral minus infinity to infinity of y, fy of y, dy. Now I notice that for any of the negative region of integration, fy of y is just 0 there. So I'm integrating 0 on the whole negative side. This is just going to turn out to be integral 0 to infinity of y. And on the positive side, this is lambda e to the negative lambda y dy. Okay, so I have y e to the negative lambda y. How do I integrate that? Well, that's just integration by parts, right? Let me take u to be lambda y. That takes care of that bit. dv e to the negative lambda y dy. I think I've used everything in my integral, nothing extraneous. Du then, y being the variable, is lambda dy. And v is negative 1 over lambda e to the negative lambda y. If I differentiate that, I get e to the negative lambda y, and negative lambda comes down and cancels everything out. Looks good. So this is uv, or negative lambda over lambda, that's just negative, y e to the negative lambda y, from y equals 0 to infinity. Here I'm being a little bit sloppy. I'm just writing y equals 0 to infinity. If we really wanted to be careful, we'd put a b where the infinity is, and then at the end, take the limit with all of our b's. But I'm kind of doing that implicitly now because I think we're a bit more used to improper integrals. So that's uv minus the integral v du. v du. Again, I have a lambda over lambda. They go away. The minus sign cancels with that minus in front and makes a plus. So I think I've taken care of the minus 1 over lambda times lambda. I'm just left with e to the negative lambda y dy. Now this first bit here, this first term, when y is equal to 0, I have negative 0 times e to the negative 0. That's just negative 0 times 1. That's just 0. So I have stuff minus 0. As y goes to infinity, I have y over e to the lambda y. Keep in mind lambda is positive by definition. So I have y over e to the lambda y. And I can L'Hopital that and pretty clearly see that that goes to 0 as well. This whole term is just 0. So let's do this integral now. Integral 0 to infinity e to the negative lambda y dy. I integrate again, I get negative 1 over lambda e to the negative lambda y from 0 to infinity. And again, as y goes to infinity, this is 1 over e to the lambda y. Lambda is positive. That bit goes to 0 minus negative 1 over lambda e to the 0, but e to the 0 is just 1. Or this is 1 over lambda. So the expected value or the mean is 1 over lambda. Or put another way, my parameter lambda here is 1 over the mean, 1 over the expected value, 1 over the average. And as kind of a random side note, in some contexts or some authors prefer to parameterize the exponential distribution differently. They'll parameterize it, they'll often use beta. They'll say y is exponential with parameter beta, and they'll do 1 over beta e to the minus y over beta, with the idea that now the expected value of y is beta. So that we don't have the expected value being like 1 over the parameter. But then, then you got to remember all these 1 overs that, so just as a little side note, kind of depends on who you're reading, how they've parameterized the exponential distribution. I think the most common way is with lambda like this, where the mean is 1 over lambda. But the other way is quite popular as well. So that is the expected value. The average, the mean, we saw through direct calculation what it is for the exponential distribution and through symmetry arguments and its relationship to the center of mass for the other three. It might not be a bad idea just to compute it for the uniform distribution. That shouldn't be a hard calculation. But again, standard and general normal distributions, we kind of have to use a symmetry argument along with just me telling you that these integrals will converge. These improper integrals will converge for these distributions. Once you get to Calc 3, you can make arguments about these integrals very precisely, and then you can really set this on a firm foundation. But that's just not something that we really have the mathematical background for at this point. But I always want to throw the normal distribution in here anyway, because it is just really such an important distribution, such a ubiquitous distribution in statistics, for very good reason too. The central limit theorem is much of that reason. Both the central limit theorem itself and essentially the philosophical implications of the central limit theorem. Okay, any questions on probability? We'll leave median and variance and standard deviation to a supplement. And again, if the probability stuff just kind of seems like a bunch of random definitions and calculations, if that's your perspective on it, that's perfectly okay. Like I said, this isn't meant to be a whole probability theory course or whole engineering stats course, certainly. But if you've had some experience with probability and stats before, you might have got a little bit more depth or a little bit more detail out of this than if you haven't really touched those areas before. But regardless, I think with this background, if you go through some of these examples and exercises when you move into an engineering stats or probability theory course, uh, seeing some of these connections, having some of this before uh, will prep you pretty well for that. Okay, now let's jump over to differential equations, kind of switching gears quite a bit here. This shouldn't be a surprise, though. Our last several lectures have been quite disjointed, right? We've been talking about just different applications of integration after chapter 7, which was kind of a contiguous amount of material where we had integration techniques and things building on one another. Then we jumped into applications of integration. So we talked a bit about arc length, moments and centers of mass, probability, things like that. And now we're on to what I suppose you could call another application of integration, although it really kind of is its own field. I would hesitate to call differential equations simply an application of integration, um, but we certainly do use integration in it. And as I mentioned, DiffEQ is at least a one semester course. You could go much deeper into it than that. And we offer the course, MAT201. I think it's a fun course to teach. I think it's a fun course to learn. One of the things that I think is fun about DiffEQ is that really depending on which instructor you take, it can feel like a very different course. Somebody can go much more applied with it and make it feel more like a physics or engineering course that has a bit more math than a typical physics or engineering course, or it can feel like more like a pure math course that has a bit of physics or engineering thrown in, or kind of anything in between. It can focus on more of the theory, more of the kind of the techniques and the tricks to actually compute solutions, or more of the kind of real life, essentially computing solving these things numerically using computer algorithms. So there are really a bunch of different ways to kind of take this course from the instructor's standpoint and even from the student standpoint. What information do you weight more heavily, or do you do more research into outside of class, uh, depending on where your interests lie and your career aspirations and so on. Okay, but this is pretty much our goal for differential equations. We're pretty much going to try to talk about four uh, subfields or subsections, I suppose, four aspects. The first is direction fields. This is a method of kind of directly getting a geometric representation of the solution of a differential equation. The next two are separable equations and first order linear equations. These are specific algebraic structures for differential equations that have kind of nice closed form solution methods, at least, most of the time. And then we're going to jump into second order differential equations, which in reality opens up just a huge amount of information. We're going to touch on the basics. And the reason we want to get to second order is that second order equations are where we see a lot of the physical applications. So things like Newton's laws are second order. They deal with forces, which deal with accelerations. Acceleration relative to position is two derivatives away. So these second order equations are really where a lot of the physics and engineering lands. Uh, that's not to say, I mean, there are certainly a lot of physics and engineering at the first order level as well, and even some at the higher order level. But, the second order, Newton's F equals ma, lands there. So we want to at least touch on it. So that's the goal. That's our goal. Now, in a DiffEQ course, we would spend more time in each of these sections than we're going to spend here. And we would cover a lot more sections that we're not going to talk about, things like series solutions to equations and Laplace transforms and all kinds of really cool stuff like that, that we're not even going to, discuss at all. But I think the goal for the 15 minutes or so remaining today will be to establish what is a differential equation. Let's get a feel for what these things are, how they work a little bit, what the solutions look like. And then when we come back next time, we'll jump into direction fields, kind of the geometry, the geometric side of things, and maybe first order equations. So what is a differential equation? Well, simply put, a differential equation is an equation, of course, relating a function to its derivatives. So we might look at an example. If I have y equals f of x, some function of x, for example, y prime equals y would be an example of a differential equation. We would call this an ordinary differential equation because it has ordinary derivatives as opposed to, say, partial derivatives from calculus 3. So sometimes you'll see it called an ODE for ordinary differential equation um, to distinguish it from a PDE, a partial differential equation, which are much more complicated than ODEs. And when we say y prime, of course, we mean dy by dx. So what does the solution to this look like? If I have a solution like, x squared equals 3 or something, x equals plus or minus square root of 3, my solutions look like numbers. For algebraic equations, my solutions look like numbers. I'm looking to find a number, or if I substitute it in for the variable, then both sides, when I simplify them, mean the same thing. What does my solution look like here? My solution, or solutions, are actually functions. Y equals f of x, right? I'm looking for a function, maybe like sine or cosine or e to the x or something like that. Then when I substitute it in for y and I simplify both sides, I get the same thing on both sides. So let's try to find a solution for the ordinary differential equation y prime equals y. And just by basically brute force, if I ask myself, what is this really asking? It's saying, I want a function whose derivative is the same as itself. Well, hey, I know such a function, e to the x. Y equals e to the x works, right? Y equals e to the x. So y prime equals e to the x, which is y, looks good. So I found a function that's a solution to y prime equals y, just essentially by guess and check or by kind of intuition. Something else that I might realize though is like y equals say 2e to the x also works. What's y prime? It's also 2e to the x, which is just y. In fact, y equals ae to the x will be a solution for any constant a. I actually have a family of functions. I actually have a family of functions where every member of this family represents a solution to this differential equation. The same way that x squared equals 3 as x equals plus or minus square root of 3. It has a couple different numbers that I could plug in and get a solution. This has different functions I could plug in to get a solution. E to the x or 2e to the x or 3e to the x or negative e to the x. Even 0e to the x, y equals 0, the constant function y equals 0. It's a constant function, so its derivative is 0. 0 equals 0. A can be 0 as well, and I get the constant function y equals 0. That is also a solution. What do these solutions look like? This might be like a equals 1, y equals e to the x. maybe a equals 2, y equals 2e to the x, y equals 3e to the x, maybe y equals negative e to the x, or negative 2e to the x, or even maybe I'll draw this one in green just so we can see it. Not any other reason I'm drawing it in green other than that the axis is already black. Even a equals 0, just y equals 0, that constant function is also a solution. Every one of these functions that I've drawn, as well as all, there's nothing special about the integers, a equals 1/2 or a equals pi or whatever, they would all be solutions to this differential equation. I have a family of functions that I get. That kind of makes sense, right? If I try to solve an equation like x squared equals 3, I have to square root. I have to do the opposite operation to kind of undo the squared. If I have a derivative, I have to kind of undo the derivative. Roughly speaking, what does that mean? I have to integrate. And when I integrate, I get an arbitrary constant. So this a here is kind of my arbitrary constant coming from the integration. I can only get an answer up to a constant of integration. Now, it's not e to the x plus a, because we're not exactly just performing an integral on both sides, and that's the end of the story. Clearly, we can't just integrate with respect to x on both sides. I would get y equals integral y of x dx. So that just kind of moves the calculus around. We have to do something different, but inherently, somehow, fundamentally behind the scenes, we're integrating to get this solution, and that's why we have this constant here. Something else we notice is that this is a first derivative. The most number of derivatives I see anywhere in the equation, there's only one term that has derivatives at all, is the first derivative. So this is a first order differential equation, or a first order ODE. It's first order because the most derivatives I have is one derivative. Now let's look at another example. We'll kind of contrast this a little bit. Y double prime equals negative y, which we could just as well write as y double prime minus y equals 0. Or it's y double prime plus y equals 0. You might even recognize this from some physics or engineering classes. This is an inertial term. It's kind of the mass term. And this can come from something like Hooke's law, maybe like a spring force term. So this could be modeling something like a mass spring system. I guess mass would be like 1 here. And if we stretch the spring and let go, the spring is going to want to restore itself to its natural length. That's going to impose a force that's going to be modeled by this term here from Hooke's law, that the further we stretch the spring from its natural length, the more it wants to pull back, and that relationship is linear in nature. And the inertial term looks like F equals ma. It's like the second derivative. That's where this comes from. So we can think of this as a model for a mass spring system like this. And we know that this motion is going to be a simple harmonic oscillator. We don't have any damping because this is a simplified version of this model, right? If I ask myself, do I know any functions whose second derivative, we now have a second order equation, but still an ODE, still an ordinary differential equation, no partial derivatives here or anything like that, no Calc 3 stuff, but it's a second order equation. Do I know any functions whose second order is negative themselves? Well, y equals sine x fits the bill. Y double prime equals negative sine x, which is negative y. Or in fact, y equals a times sine x works just fine as well. So if sine x or really any constant times sine x would be a solution here. Note that y equals 0 is a perfectly good solution. We just kind of set the system at equilibrium where the spring isn't stretched or compressed at all and just let it go, and it's just going to sit there and do nothing. So that's perfectly fine. But I also notice, and I'm not putting this in red for any reason, that I ran out of colors, y equals cos x also kind of works, right? And cos x and sine x aren't really the same function. So it's not just like I have the same function written again in a different way or something. They're really fundamentally different functions. Or again, really a constant times cos x would work just fine. In fact, even a combination of these will work. A linear combination of these will work because the derivative is a linear operator. It splits sums apart and kind of can operate on them independently. My writing is getting worse and worse. So y double prime is negative a sine x minus b cos x, which is negative y. I actually realized that I have two constants, a and b, that I can choose. This again gives me a family of functions, but where I can choose a any way that I want and b any way that I want. Two constants. Why do I have two constants? Well, this is a second order equation. I didn't actually do any integration here, but I can imagine kind of philosophically in the background, to undo two derivatives, I kind of need to do two integrals, each one of which contributes an arbitrary constant. So a and b are my arbitrary constants coming out of that two iterations of doing integrals to kind of undo these two derivatives. Again, I didn't do any integration directly here. This was a guess and check, but that's philosophically where these are coming from. And these would combine together to make a single trig function with a given amplitude and potentially a phase shift. So this is a simple harmonic oscillator. It just operates like a standard trig function with a certain amplitude and a certain phase shift related to this choice of a and b. We would use the parameters a and b to tune the model to the system. Do I start with the spring stretched this way or compressed or stretched even more? Do I start by pushing the mass, giving it an initial velocity, or does it start at rest? Right. Or over here, I might pick maybe a value at time or position 0. And that might, maybe if I'm using this as a population growth model, I look at my population at time 0 here or position 0. And depending on what my population was, my initial population, that might pluck out one of these functions from this family that I'll choose to use to model that circumstance in a different situation would call for a different member of this family. Okay, so that is a super quick introduction to differential equations. Let me stop the recording.